45 kilowatts. In horsepower, that means 61.18 horsepower. Let's compare it for a second to the king of e-motos right now, which is the Stark Varg. The base model Stark Varg has 60 horsepower. My built Surron battery that I'm going to show you here has 61.18 horsepower. Yes, that's more horsepower than the base model Stark Varg. Next, let's compare it to a 250 4-stroke. The 2024 GasGas MC250F has 41.9 horsepower peak. My Surron 80 volt battery that I'm going to show you in this video has 61.18 horsepower. Yep, you read that right. The Surron battery has almost 50% more horsepower than the GasGas 250 4-stroke. Or let's look at all the new 250 4-stroke bikes. In a 2021 comparison test, the most powerful 250 4-stroke had less than 45 horsepower. Again, the Surron battery pack here has almost 50% more power than all stock 250 4-strokes. And yes, even the 250 factory bikes have less power than my Surron battery that I'm going to show you here. Okay, but I know the question you're asking. What about the other components in the drivetrain? Can the other components handle that amount of power? Let's talk about controller. The X9000 version 2, which I have on my dirt bike, that can do peaks of 45 kilowatts. The XLB60 Race is advertised at a peak of 42 kilowatts, and I have seen some pull records with that motor showing even more than that, around 43 kilowatts. So the XLB60 Race, the air-cooled version, is pretty close to it. The water-cooled version may indeed get us to 45 kilowatts. What about Torp motors? Torp has their new TM40, which they advertise at a peak of either 42 kilowatts or 50 kilowatts, depending on the version. I've not seen pull records to verify these power output numbers, but if they're true, then yes, Torp TM40 can indeed do 45 kilowatts. And finally, before we get into the build video here, let's have some fun with power to weight ratios. I just want to show you some things that are going to pretty much blow your mind. Let's first look at that GasGas MC250 again. Here's the power to weight ratio of the GasGas 250. At 41.9 horsepower, the bike has 31.24 kilowatts, but it weighs 101.7 kilograms or 224 pounds. That's about on par with all 250 4-strokes. So the power to weight ratio for this GasGas, which is by no means a slow bike, is 0.412 horsepower per kilogram. Not bad at all, right? I think no one would argue that's a very quick bike. Now, for more comparison, let's look at the Stark Varg, the base model, the 60 horsepower one. Of course, again, we're at 60 horsepower. In kilowatts, that translates into 44.74. But Stark Varg is a heavy beast. It weighs 118 kilograms or 260 pounds. That gives the Varg 60 horse version 0.508 horsepower per kilogram. Not bad at all, of course, and nobody would argue that the 60 horsepower Varg is still a very fast bike, and it has an even better power weight ratio than the GasGas 250. But here we go. Let's look at the Surron. So let's look at a modded Surron LightBee. I'm not saying this is my bike because my bike with a KO motor cannot do this power level, but let's look at the ultimate theoretical modded LightBee with all the highest end components now, including this battery that I'm building here. So we're at 45 kilowatts, which this battery can definitely do, and you'll see that later in the video. That translates, like I said, to 61.18 horsepower. The bike weighs 65 kilograms approximately. That's 143 pounds. That gives you a ridiculous power to weight ratio of 0.941 horsepower per kilogram, or in other words, over double the power to weight ratio of the GasGas bike and way more than the power to weight ratio of the Stark Varg. Now I know what you're saying, 65 kilograms, that's kind of light for a built Surron. That's the weight that I calculated for my bike, but even let's say if we have a little heavier bike, a little bit more weight, let's look at 70 kilograms here. Same power of course, but if you have a 70 kilogram bike, you're at 154 pounds. That still translates into a crazy 0.874 horsepower per kilogram. Way more than the GasGas, way more than the Varg, and just an absolutely nuts power to weight ratio. So with that out of the way, let's get into the battery build. Ampace JP40. Why build a pack with JP40, and why build one with tablet cells in general? And who needs a LightBee that can do 45 kilowatts? Well, after I tested the JP40, I was totally blown away by its performance. It was, by far, the highest performance cell that I've ever tested. And I decided I had to build a pack with these cells for my Dirt Beast. If you haven't already, please check out my tabless videos on the channel. The very short version is that tabless cells, and the JP40 in particular, have higher performance than any tab cell, and that includes the mighty Molicel P50B. They can push higher maximum amps, and they have less voltage drop and less temperature increase than traditional cells. When I realized that the JP40 was a current state-of-the-art for PEV batteries, I just had to build a pack with them and see for myself how they performed. You could say that I'm the guinea pig for using tabless cells in a Surron. And now, here's that pack build. Sit back and enjoy watching. This one's a little bit historic, as it's one of the first tabless battery packs that's ever been built for an e-moto. Okay, the first Ampace JP40s have arrived. Took the long boat from China straight to Ukraine here. These are, sorry about that, these are LT labeled ones. I got all LT instead of the Ampace version. These are going to be for the upcoming new Surron battery pack build that's going to be capable of 630 amps plus and 48 kilowatts. I popped them when they were cold on the tester, a couple of them, and they were reading right around 2.9. I heated up a couple for a little bit. Let's see how they do now. So yeah, actually it does make a little difference, even on ACIR. These were reading like 2.9, all of them when they arrived and the box was cold, pretty much frozen, and warmed up a little bit on the heater. No, just by feel, I'd say they're like 28, 29 degrees Celsius. And 257, let's see where the other one is at. And how's that for consistency? 255, 56, 57. Awesome. That is a great internal resistance reading, so very happy. Now we got 2 more boxes coming from China, and we'll be able to get started on the next Surron battery pack. Third group came 68. I didn't take a photo of how they arrived. They were all thrown around. Only about 2/3 were together here. The rest were kind of loose, laying everywhere. I could tell the box was, when I shook it, I heard. So the JP40s all made it here okay, thank goodness. Was a little dicey with some of them. No, because we weren't shipping a full case because of Ukrainian customs being effed up. Normally you would just ship a full case of these, 100. But because Ukrainian customs is effed up, we sent them in groups of under 65 each for customs. Anyway, they moved around in shipment, the packaging. No, Boot Energy, they did a great job trying to pack them safely, but in general in the future, I think they got to be just pushed close together and fill this with cardboard. But anyway, thank God none of them, touched together, shorted out. They all made it here okay, so that's great news. We have our JP40 battery kit ready to go, and next step is putting in here holders and testing all cells, make sure we're okay for voltage and internal resistance. So a little bit of an interesting thing here occurred. I'm going through and doing my usual cell checks before the next step, which actually you can do in the box. It's probably a better idea. I don't know why I don't do it in the box. Anyway, doing the cell checks, 2 things I noticed. First is there is more voltage variation than I'm used to. These are the Ampace LT. With the Samsung and the Molicel, usually they're within like 1/100th, and this is the checking is just a formality because they're all perfect. On these, I'm seeing more variation from 347 to 354. Most are right around 350 plus or minus 100th, but I am seeing as low as 347 up to 354, so just to note they had a little variation. But what's really weird is this guy right over here, that one, I'm going through measuring and I see 363, and I'm looking, I'm thinking, no, it's got to be wrong. 353, check again, 363, check all the other ones around it, they're like 350. One cell is 363. And I didn't test it, I didn't charge it, I didn't do anything. So one cell is a full 10th higher than the others, which is really weird. I haven't checked this block yet. But anyway, just initial observation, more voltage variation than Samsung or Molicel. And one, I'm going to have to discharge and get it to match the others because it's a full 10th more than all the other cells, which is really weird. So anyway, decided to pull everything out. Yeah, had to do it out of the box. And check IR this way. Anyway, because this probe, I can't do it when it's in the battery pack. They're so far all between 275 and 285. Have to compare that to my other Ampaces. I think it's slightly higher. They're all measuring consistent internal resistance, which is great. 275 to 285 means they're all genuine. Voltage, like I said, had a little variation from 347 to 353, except for this guy. 363 volts. Very strange that this is a full tenth other than everything else, but its internal resistance is okay, at the higher end of the tested, but still within the range. So this one I'm going to have to discharge to get the voltage to match. Okay, finished all the testing, and the results are a little bit troubling. I mean, it's not terrible, but not what I've seen from Samsung and Molicel. Okay, long story short, IR was really quite consistent and all low, so they're all genuine. They were between like 265 at the low end and 285, but they all, were quite consistent, so IR was fine. But I do see a voltage variation that I've never seen with Samsung or Molicel. I've had two cells that are high, 364. I mentioned they're all like right around 350, 352, 353. I think that's the spec. But I had one that was, 364, and then I had one that's 357 or 6, something like that. Two that were a little too high that I'm actually going to discharge. And then this one is the outlier on the low end. This is 344. Keep in mind, everything else is like 350, 351, 352, 353. So if I hadn't checked these and hadn't done anything and just thrown these in the pack, this I'm actually going to have to put on charge a little bit. If I hadn't done anything in these 198 cells, I've actually had standard voltage, like I said, like 350, 351, 352, right around there. But I've had from 344 to 364. So actually a 0.2 volt variation in this group of 198 cells. So that, to be honest, it's a little troubling because, like I said, with Samsung, I almost never had to check them because they're like within 1/100th, even 5/1000ths of a volt. They were so consistent, Samsung. And Molicel's the same thing. Like the most variation I had was 1/100th. In these cells, I've gone from 344, one outlier, to 364. So it's a little troubling. I mean, I'm not saying it means the cells are bad. I was speaking with Mooch a while back about these, and he said he noticed some of the Ampace had self-discharge issue. I mean, they self-discharged faster than the others. Maybe that's just part of the whole tablet, saying that these have probably they've been in transit for 2 months and they may have been in storage for several months before that. So these may have been manufactured 5-6 months ago. It's possible that they just have slightly different self-discharge rates. But I do have to note that for me, from seeing Samsung being 0.01 or 0.005 variation and seeing here two outliers that actually give a 0.2 volt variation from the lowest to the highest, to me it's a little bit, not worrying, but just a little disconcerting, I would say. So here we are. Two that were a bit too high are on discharge to get them down to 350, and this one that was low, I don't know why it keeps turning off, charging. Okay, everything checked and manually voltage balanced. Now back to my favorite activity, pounding. I love to pound. I have one cell here that I marked. Don't know if you can see, it's kind of hard to see on here, but one edge of it, the right side there you can see, is slightly dented. Just a little bit. It goes down, hard to see there, but this corner is dented at the edge here. Okay, so well underway here, and it's been a little more of an exciting / eventful start to pack building than I'm used to. Mentioned in the previous segment about there's been a bit of voltage variation in these. I just want to say, I'm not expecting these to be Samsung or Molicel. I'm expecting them to work properly and be safe, but I'm not expecting the absolute, level of polish that you would get from, say, Samsung, because, well, it's not Samsung. It's more of a third-party brand, not a first-tier brand. That said, also, what I forgot to mention before is considering the price I got these for is an absolute ridiculous steal. I'll put links to my supplier in the description again, and I've mentioned this in the other Ampace videos, but my Alibaba supplier had these cells which have a little bit of a, you see that? A little imperfection on the labels, just a little bit of kind of running ink on the labels there. I don't know if you can make it out. It's really almost not visible on most of them. Anyway, because of this cosmetic imperfection in labels, I got just a crazy price on these. I think I paid about $2.50 each, maybe $2.55, something like that. So just an incredibly good price for these. So for that price, I just want to say I'm super, super happy with them. I mean, as long as they perform okay, IR has been great, so that's awesome. One other thing too, and again, I just want to talk up my bus bars and spacers thing here. Oh, got to talk about bus bars for a sec too. I want to talk about the bus bars and spacers because one good thing about it, if you have a bad cell or problem later on, like I said, you can cut it out and remove the cell. Now, what happened here? This wasn't a bad cell, obviously, they're all brand new, but as I was doing these stickers, I noticed that one cell, if you look closely here, it has a little ding on it, a little dent, just on the corner of the negative terminal. I know it's kind of hard to see there. Just a little, there you can see a little dent on the corner. I don't know if this happened in shipping or if it happened while I was doing my tapping to level these out. But anyway, little dent on the corner. So unfortunately, I didn't order any extra of this batch of LR2170 LAs. Oh, because of Ukrainian customs. But anyway, couldn't get any more without having customs tariffs. Luckily, I do have 4 of the JP40, of the LT version, on hand here. So I'm gonna, just to be safe, I think probably would be okay, but I don't want to have any kind of dent, physical damage on the cell at all. If you can see, I know it's kind of hard to see, if you can see that little ding on the side there. So I'm going to replace this with one of my original test cells, test JP40s, to see how that performs. I mean, not to see how that performs, but I'm sure it'll be fine. But anyway, it does have a couple cycles on it. So this one, because I don't have any extra new ones, is going to get replaced with one of my test JP40s. Okay, and without trying to make the video any longer than it already is going to be, about bus bars. I need to talk about bus bars just for a second here, because I've done a lot of thinking, a lot of discussing, hand-wringing about bus bars. I mentioned in the JP40 videos I've done that if you build a pack, spec'd for higher amps, 500, 600 amps like these can do, you need to kind of upgrade everything in the path, your internal wiring, your connectors, your BMS, and yes, the bus bars too. So originally, I was speaking with my manufacturer and with some engineers about these two, was planning on doing some upgraded, beefier copper nickel bus bars to handle the higher amps. These are 0.3 millimeter copper nickel, no copper, and then where you weld is a copper nickel sandwich. I sell them on the KILOWATTS, my KILOWATTS site. We rate them conservatively at 300 amps. However, I've had a number of customers using them on 400 amp battery pack builds without a problem at all. So anyway, the issue is that I was going to try some thicker 0.5 millimeter bus bars for this build, just to be safe, to have a little bit thicker bars and a little more capacity, amp handling capacity. However, at the time that I went to order, that I was ready to order, it was the Chinese New Year holidays, and it would have been a 1 month delay. If you consider the time that they were off for holiday, plus manufacturing, plus shipping, I would have been waiting a month to get those bus bars. So I really debated about waiting, thought about it a lot, talked more with the engineers, and here's the bottom line. And again, I'm going to try to make it as brief as possible, not take more time. I'm going to go ahead and use my standard but thick 0.3 bus bars, high power bus bars on this, and I think it's going to be no problem at all. Here's the thing. I'm going to put on screen here the discussion of the amp carrying capacity. There's a lot of discussion online about how many amps these can carry at different thicknesses and all that. Well, there's kind of a formula for it, and you take the cross-sectional area. So what does that mean, a cross-sectional area? Well, if you think about that these at the narrowest point are about 115 millimeters wide at their narrowest point, times the thickness, which is kind of hard to see there, but the actual thickness of 0.3 millimeters. You take that 115 by 0.3, you multiply it, and that comes up with your cross-sectional area. I'm going to put on the screen, I think it's about 35 square millimeters. So that's how you calculate the cross-sectional area and the amp carrying capacity. So anyway, that's how you calculate the cross-sectional area and the amp carrying load. Like I said, based on that, these should be able to handle 600 amps no problem. It's equivalent to, you know, more than 2 6AWG wires. I know myself, and I know, to be honest, from my past riding, the most that I usually pull, even on peaks, is about 17, 18 kilowatts in hard trail riding. About the bus bars and how many amps I'm going to be pulling. So I described and explained how many amps they can handle based on the cross-sectional area, what AWG wire that equates to, went over all that, and have to be realistic about my real-world riding on this bike. I rode the dirt build all last year. I found that at hard trail riding, the most I was using when really getting on it was about 17, 18 kilowatts. And when I went on the motocross track here, which has really huge uphill sections, I think the most I was pulling then was like 23 or so, maybe 23 and a half, 24 max. So that translates into only about 250 amps peak. On trail, only about 200 amps, about 250 amps on the motocross track. So I know realistically from my riding, my skill level, even though I plan this year to upgrade the motor to install my XLB60, to install the extended swing arm, to kind of, you know, make it a full sort of more race build. I know that realistically, I'm not going to be pulling 500, 600 amps pretty much any of the time. I'm going to try to do some testing and pull as much as I can. But anyway, long story short, I know that realistically I'm not going to be pulling that much. So I am going to use my 0.3 bus bars, still speccing the battery for a maximum of about, 640 amps is 70 amps per cell, 60 amps per cell is 540 amps. So in general, I think I'm going to spec it for now at 540 amps max peak, but we'll see. Okay, I interrupt this video to do a quick segment here about what I call cross-sectional area current carrying capacity. It's a mouthful, I know. What are we talking about here? We're talking about bus bars and how much power that they can handle, how much current that they can put through. These guys right here. And what we're looking at is the cross-sectional area. Hope that focuses. That is how wide it is here, the width times the thickness. The cross-sectional, the total area cross-section determines how much current we can carry safely. So, with our standard 0.3 millimeter bus bars, that's these guys right here, they are at the smallest point 115 millimeters wide approximately times 0.3 millimeters thick. That gives us a cross-sectional area of 34.5 square millimeters. Now, I've spoken extensively with the engineers at our manufacturer and at other manufacturers of these bus bars, and the agreement is that the power handling capability is between 20 to 25 amps max. That's how the max current you should carry on these. So at 20 amps, that comes out to 690 amps max, which is a lot. At 25 amps, that's 862 amps max. So you can see, talking 300 or 400 amps, we're well within the capability, even if you discount these numbers by like 25%. Now, as an anecdote here, I've used these bus bars at 320 amps max on my dirt build for over a year now, no problems at all. I have other users of these bus bars that are pushing 400 amps peak, 400 amps max, I should say, with them, no problems at all. My new street build with the Model Cell P45B is doing 405 amps max. So I have no question at all that these can handle 320 to 405 amps, no problem. Actually, they should be able to handle 5 to 600, which is why I was really debating about using these on this build. I think they would have been okay, but to be safe, for extra headroom, I decided to go with a 0.5. So let's do the calculation for the 0.5. Same width, of course, 0.5 millimeters thickness. That gives us 57.5 square millimeters cross-sectional area, almost double the 0.3, which is great, and that gives us a a power handling max capacity of 1150 amps at 20 and 1437 amps at 25. So yeah, like I said, even if you discount those numbers a little bit, we should have no problem at all handling the 500 to 600 amps maximum that this pack has. Okay, now for a basis of comparison, let's compare it to something we're all familiar with. That's 6 AWG copper wire, right? Like we use in our wiring harness, our QS8 connectors for the Surron. So 6 gauge copper wire that has a 4.11 millimeter diameter comes out to 13.3 square millimeters for the cross-sectional area. And how does that compare? How do these bus bars compare in terms of 6 gauge wire? Well, it works out that the bus bars are equal to about 2.5 6 AWG wires, or you could say 2 6 gauge wires plus 1 8 gauge. So a 0.3 copper bus bar, that's like having 2 6 gauge wires plus an 8 gauge wire. That's about the same cross-sectional area, to put in perspective. Now keep in mind that for your home electrical box, you also have copper bus bars like this, like for example a bus bar that would tie together all the negatives in your electrical box. Those are rated lower than 20 to 25 amps per square millimeter, so keep that in mind. Also keep in mind that this calculation doesn't take into account the length. You know, how long your wire is also going to determine how much it heats up when you put that current through it. In our Surron bus bars here, the longest length that the signal is traveling, which is this way, that the current is traveling, is about 80 millimeters long, so we got a really short length. Think about it in terms of 6 gauge wire. For example, if you have an 80 millimeter, 8 centimeter long 6 gauge wire versus 10 meters, of course a longer length is going to have more resistance and it's going to heat up more. So we're talking about, of course, short lengths with the Surron. And also keep in mind that this calculation doesn't take into account time, how long that current is being applied, peak versus continuous. I'm really talking here about peak because in most cases in like a e-moto use, you're not going to be pulling 400 amps continuous for a really long time. We're really talking about kind of short bursts and peaks here. So anyway, hope that wasn't too boring. Hope it gave you some useful information about just how much current these bus bars can carry. But forgot to make one more very important point though related to that is I am going to be manufacturing these in the thicker, super heavy duty 0.5 millimeter thickness. So those will be on the site. I'm sure by the time you see this video will be the standard heavy duty 0.3 and the super heavy duty 0.5. I do recommend, if you're going to be building a tabless pack for a super heavy duty use, I'm talking about, supercross racing, motocross racing, professional, semi-pro, or drag racing applications where you're really going to be pulling, super heavy loads. You're really going to be testing these at say 60, 70, even 80 amps per cell and pulling like 600 plus amps from the pack. Then I definitely recommend using the 0.5 millimeter. I'm not trying to say that everyone, doing tablets with super high output should be using 0.3. No, I'm saying that in general, it's better to have the 0.5, have a little more, margin of error, margin for safety, a little more current handling capability. And if you're going to do, like I said, a super high drain, super high load application like that, definitely go with the thicker bus bars. One other quick point to make, I forgot to say, is the spacing also, just to fit these in on a Surron, if all of these are 0.5, that's adding 0.8 millimeters total to the length of the battery. The length is this end. This is front to back. Front to back is the length, and this is actually the tighter dimension. In my metal case, I actually, after the last pack was done, I only had about 1 millimeter free in this direction. So I'm going to be, by going to the thicker, you're going to be adding 0.8, so it's going to make it a very, very, very tight fit. It should fit okay, but it's going to be even tighter. The other potential issue is, because it's going to be thicker on your welding pads too, it may be an issue with welding. You may need to get a stronger welder. You may have to use a lot of power on the welding and heat up the cells a little bit more, which you don't want to do. So that's just one thing to keep in mind, that with the thicker bus bars, you're also going to have to, use more energy for your welding too. Okay, that's it. And now how about some real power numbers? What you're seeing here on the screen that's sped up, this is a segment from my Samsung 50S video showing the real power calculation for the Alta Sigma and the eRide Pro SR, where I also discussed the JP40. Check out that video if you haven't already watched it. The great thing about all the work I've done on this channel and the hundreds of hours I've put into testing these batteries is, now we can calculate the real maximum power of any bike or any battery pack. And that's including voltage drop. This is important. And we can now know the real power numbers without all the marketing hyperbole. Okay, so let's go over calculating what the real maximum power of this beast battery pack is. Before I do that, really quick, here is the calculation on the street build, and that's the P45B pack that I finished recently. I think you can see this calculation in detail in the P45B video. It's also going to be in the street bike build video, but short version is these are both 80 volt 22S9P. The street bike has a model cell P45B, and of course the dirt bike now we're doing is with the JP40, but same configuration, smaller BMS. On that one, we're running at 45 amps maximum for the P45B, and the voltage drop is 3.53 volts at 45 amps. So the real maximum power that pack is going to put out is about 31.4 kilowatts. You can bump up the amps a bit to get it a little bit higher, but the spec that I'm building at 45 amps peak is 31.5 kilowatts. So you can see this in more detail in that P45B video or the street build video, which I promise is actually going to come soon. So now, back to this beast, JP40 pack, real power. But again, before we go over the calculation, there's just one thing I need to recover quickly. Everybody probably, hopefully already knows this, but just need to go over it quickly just in case that's not the case. So, for maximum power, what is the limiting factor for our maximum power? What limits our maximum power level? Your max power is limited by the lowest of these components. The battery, which has traditionally been the weakest link and the least powerful component in PEVs, the controller, or the motor. And actually, your connector and wiring harness can even be a limiting factor as well. So let's talk about this build. This is going, of course, in the dirt build that you guys have seen the video of before. I'll show on screen here as well. So currently, the dirt build has as the motor the KO-RS, of course, and that is definitely the weak link in this build. The KO, when it was being produced, when KO was still kind of alive and producing it, they claimed 35 kilowatts for this motor. Well, they can say ha to that because it's not true. Jared at EBMX has tested pretty much every motor on the market, including this one, and he's shown that the maximum of the RS is about 26 to 27 kilowatts in real life. Otherwise, it'll just overheat or demagnetize or both. This bike, of course, has a controller, the X9000 version 2. Now that, we're talking about battery amps here, not phase amps. The max normally that can handle is 500 battery amps. However, you can kind of hack the X9000 to let it have short peak bursts of 600 amps, but not continuous. It'll overheat if you run it 600 for too long. So anyway, the X9 version 2, it can definitely handle this 43 to 45 kilowatts. That would be 80 volts at 500 amps or 80 volts at 600 amps. So the X9 is not a limiting factor. Now the connector though is my single QS8 that I'm rocking on this build, and put on it when I built this a year and a half ago. Although it would certainly be very fun and entertaining and smoky to see it putting out the 500 to 600 amps through that connector, I'm sure it would be fun to watch, but yeah, it's going to be a pretty smoky event. So actually, in reality, even 300 amps, the max that this bike has now, is too much for a single QS8. So the solution, my solution for this build, as you'll see, is dual QS8s. That's the way to go on here. You may be asking, why not use a bigger one? QS10, it can handle more. Well, if you've seen them in person, they are totally huge. It's almost like the size of the palm of your hand, so not really any space to fit two or even one of those under your battery lid if you want to have a battery lid on it. So anyway, that's the maximum power limits. Now that we've gone over that, let's do the power of this pack. Okay, so now let's finally calculate the real power of this beast. So we're talking Ampace JP40 tablets. This battery, as I've said, it's 22S9P, like all the batteries I built for Surron. That's 80 volts nominal, 92.4 volts fully charged. Ampace JP40, our BMS is a new, larger one. You'll see here in the video, 340 amps continuous, 850 amps peak, so the BMS can definitely handle whatever the cells can put out. Now the JP40, if you've seen my testing and you've seen, read about the discussions about it, these can do 100 to 120 amp plus peaks easily, short peaks, no problem. However, it's safer to set the maximum lower than that, in my opinion, and I think other people would agree, to set the maximum lower, say to 60 amps, and in that case that would be 540 in a 9-piece, 60 times 9, or 70 amps peak, which would be 630 amps max for the pack. No, for safety, for longevity, definitely the cells are going to last longer and you're not going to heat them as much, limiting the peak power to a lower number than what they can do, 120, 140. And just for my sanity, not worrying so much about putting so much power through all these components. So I decided for the power spec, the design spec I should say, for this pack, to set the maximum to either 60 or 70 amps. And you can see here in a sec, I think it's going to end up kind of between those two. Now, the good thing is, from all the testing I've done on the KILOWATTS channel here, the testing of basically every 21700 on the market, we can know the actual power output of this pack because we know the actual voltage drop of JP40. I'm going to put some charts on the screen here from my previous testing. But let's quickly calculate the power. So, as everybody should know by now, watts equals amps times volts. Calculating now our amps for this pack, like I said, if we go with 60 maximum for the cells times 9, that's 540 overall for the pack. If we go with 70 maximum for the cells, that's 630 amps max for the pack. In my testing, I tested the JP40 and the other tablet cells up to 60 amps max. My equipment, even using two testers together, I can't do more than that. So I only tested it to 60 amps to get the actual voltage drop. Now, the thing is, manufacturers, cough Altus, cough E-Ride, manufacturers might like to lie, I mean embellish their specs to say that the power rating of this bike or this battery pack is, let's calculate it here for a second. So we know we have 540 amps, we know the peak voltage, right? Full volts, 92.4. They might say that the power of this pack or bike in it, the bike that the pack is in, is 540 amps times 92.4 volts. Wow, that's incredible, 49,896 watts. Or even at 630 amps, which we know the cells can do quite easily, times 92.4 volts, that's incredible, 58,212 watts. But the thing is, manufacturers, like those will be unnamed. Actually, it's not just Altus and E-Ride. Lots and lots of manufacturers do the same crap, which is embellish or lie, however you want to call it, their specs. The thing is, these power claims, they do not take into account voltage drops. So basically, if you were to claim this power, it's a lie. The actual power output, let me move my sheet up here for a second, the actual power output measurement must, I should have underlined that, include voltage drops. So let's do that for this pack and this bike. JP40s at 60 amps in my testing. 60 amps, keep in mind this is a huge load. This is very, very high load for any cell. The initial voltage drop is 3.50 volts, and that is actually a big voltage drop. It's less than 3.6, which is nominal, less than 50%. So even a very powerful cell like the JP40, when you hit it with 60 amps, a high load, it has a decent amount of voltage drop. Now keep in mind, this voltage drop is actually the best, I should say the lowest voltage drop of any cell that I've ever tested, of any cell that's on the market now. So that 350, other cells are going to have even more voltage drop. So now we can calculate the real power output, the real voltage. So at 60 amps, you're at 3.50 volts, 22 times 3.5, 77 volts. So that's going to be your pack voltage when you hit it with 60 amps, 60 amps times 9, 540 amp load on the pack, the voltage drop after 5 seconds. So we're at 77 volts, so now we can calculate our true power. 77 volts at 540 amps, and that's again 60 amps per cell, that's 41,580 watts, so about 41.6 kilowatts. Now if we take it up to 70 amps, 77 volts times 70 amps, which is 630 amps total for the pack, is 48,510 watts, so like 48.5 kilowatts. But actually that's not really true. It'll be a little less because we're going to have a little more voltage drop at 70 amps than 60. But again, I didn't test at 70, so it'll actually be a little less than that. But let's take, so we're at 41.5, 48.5, and I'm calling this a 45 kilowatt pack, right? A 45 kilowatt maximum pack. So let's go between those two. What if we go 590 amps total, 590 amps max for the pack? There you're at 45,430 watts, and that comes out to 65.55 amps per cell. So I think that's a good actually max to cap it at. Of course, again, you're going to have a little more voltage drop because we're over 60 amps, but again, this is 45,430, so I think we can safely say right around 65 amps per cell, we're going to be seeing that peak maximum, that true maximum of 45 kilowatts. So it is definitely, in reality, with voltage drop, a 45 kilowatt pack, which is pretty amazing for how compact and how light this battery pack is, and how light the bike is. So that's it. That's the actual voltage calculation, the actual power calculation, and I hope it was informative and not too boring. Okay, so something super important for this battery pack build came today. Been waiting for it for a while, and that is these guys. These are the new SUPER-BEEFY Super Heavy Duty. Don't know if you can see there the thickness. These are our new SUPER-BEEFY bus bars. They are 0.5 millimeters, which is, let's look at them sideways here, which is almost double the thickness of the standard bus bars. Our standard bars, which we've tested up to 400 amps, are 0.3 millimeters. These guys are 0.5. So just by feel and touch, I can tell they're a lot thicker, a lot heavier duty. Hopefully going to be able to solder on them okay and weld them okay. I'm going to go over a section here that I call quick lesson on cross-sectional area and amp capacity. Our standard bus bars can easily handle 400 amps. In fact, they can handle more than that. I'm going to go over that in a second about the cross-sectional area and the amp capacity. But just to have a little more headroom, and because this pack can do, you know, up to 600, 650 amps, I decided to go with these extra heavy-duty bus bars. They do feel quite a bit thicker. Okay, so I'm finally doing what I say to do, but haven't done in the past. That is soldering everything first. So this is B+ plate. I marked dimensions where it's bent and everything, got it ready, did the bend, and going to do 2 B+ wires with a big soldering iron. That guy over there. Going to use that big soldering iron there. Do 2 B+ wires because the huge amp load. Going to do one on this side, one on that side, and get everything soldered on before welding it on the cells. Well, that was, I would say, not super fun, but at least using that beast, got them both soldered on there okay without putting heat into the cells, and I think it'll hold on okay. Now, about doing this for B- soldering in advance. This is very difficult because these wires would need to be placed in their exact finished place and soldered on there like how it's going to be when the pack is like almost finished. Obviously better to solder everything on now before it's welded. I'm going to give it a try and see if I can do it with you know, connecting in advance. If not, I'm just going to do the pads on here, and then I'll have to just solder them carefully at the end. Okay, and here's the connection minus bar. That is going to get these guys going across. Okay, well, half of the connecting plate is done. Not super fun, but at least much better doing it here on the bench than on the battery pack. So got 3 of them on. Unfortunately, I can't do the other full connection because, well, that has to be done later when after the packs are married, the blocks are married. So just on the other one, I'm going to do tinning, solder pads, and I'll do tinning on these 2. That's hot. So for connecting pieces, there we are. Connecting pieces are going to go like that. Like I said, can't connect them now because it has to be done after the blocks are together. Okay, I tried doing it. B- BMS off the pack. We'll see if it fits okay. I would not recommend this if it's your first battery pack doing it this way. It's kind of very advanced thing I'm doing because I've already built several of these and I know pretty much exactly where these wires have to go. Because if you get this wrong, this will be sitting too high or off to one side. So anyway, we'll see. Hopefully it works okay. Hopefully I don't have to desolder them. Okay, so the question is now, is it going to fit on the pack okay that I've already pre-soldered these? I think it's going to be okay. There's a little bit of, you know, flexibility, room for moving back and forth side to side. Remember, keep in mind, this is the Monster Ant BMS 340-850. It's actually a little bit too big for the case. It's like 161 millimeters long, which is the same length as the case. So it's going to be in a custom 3D printed cap, and which is going to stick out in front a little bit. So this is going to go, oops, sorry. This is going to go like directly parallel with the back of the pack. This is the back side here, the back end. And this is going to stick out front a little bit. So hopefully, about height, I'm not too worried. If it's a little higher, it's no big deal. Hopefully, it's going to fit okay, and it's going to go on here is B- on the pack there. So it's going to go like that. So we're going to weld it, and then hopefully, you know, as long as it fits okay, it's great because then this is obviously, you know, was a lot of soldering, a lot of heat put into there, so won't have to resolder and put any heat into the cells. Okay, so here's how the pre-soldered stuff looks. There's that. Got this guy, that one, and here. Yeah, it's kind of a pain in the ass to have to do all this first beforehand. You know, when you're at this point on the battery pack, you want to like get welding and get that all done, make some big progress. But I think it's really, especially with these cells, because it's kind of an unknown with tablets, really better just to, you know, take this extra step in advance, do it, and not heat up the cells. Okay, so I've just started my welding on the tablet cells here, and I have to admit I was pretty nervous about doing it just because, you know, obviously this is the first time doing this on a tabless pack, and you know, nothing really to be nervous about. This little welder, the Minder RC, doing it perfectly. I just set it a little bit higher to like level 15 rather than 13 because this is, you know, the 0.5 copper, not the 0.3. Welding, no problem. You know, they're holding great. The welds are perfect. The one thing to note, if you can see on there, I don't know if I can focus with this closer, because remember, like I mentioned, you're not supposed to weld right where these little spirals are. Oh, let's get better light. You're not supposed to weld where these spirals are. So if you notice here where my negatives are, I'm kind of like doing a semicircle, like the outside two are closer in, and then the middle where the spiral is are further out, so it's kind of like two crescents. And there's the, so just being careful, you know, not to weld right close in that center part, but you can actually see the little spiral through the slot there, which is great, and it's not hard. So I have to say, you know, so far welding these being tablets and with the thicker bus bars, no real issue at all with it, so that's great. So one block down and one to go. No problems at all. It went pretty easy and straightforward, so that's good. The welder does the 0.5, no problem. No issues with welding the tablets, so no, everything went really well. Coming along. Okay, everything except B- is welded on. Went without any problems, which is good. B- is going to be a little tricky this time because the BMS is on there, so got to do it carefully, no shorts. But yeah, no problems with welding the thicker bus bars and the tablet cells. Everything went okay, which is great. Okay, and that's it, all welding done. B- with the BMS attached is on successfully there. Kind of did it very carefully, so nothing shorted out. Yeah, so was able to do it with pre-soldering everything. Seems like it went okay. And next step is marriage. Marriage is in progress. Almost didn't forget to do these in time before the marriage. Well, these spacers, not really spacers, support blocks, no, they're not, I guess, an absolute must. I strongly prefer to have them, to put them there, just so you have a nice even weight distribution in the bottom, because there's so much weight on the bottom. So I highly recommend, just as one little step, but important, to evenly distribute the weight on the bottom of the pack. Use these little support blocks that I made. Yeah, just much better like this. Pack is, all the weight on the bottom is now being supported across all the spacers instead of just being supported on 3 cells. So I definitely recommend doing this. Okay, well, that went mostly okay. No, got the 2 married. Only little problem is my one side is like 0.5 millimeter, no, this way, higher to the left than the other one. As soon as I put them together, this tight bond just gripped and I couldn't move them at all. So there was like no flexibility. Anyway, we'll see if my method that I did with pre-attaching these and pre-doing the solder pads works good. Gonna now do a quick solder and hopefully won't heat them up too much. Had to put on the gimbal because my hands are shaking after doing that. To be honest, it was still a little ass cheek tightening to do this way. I mean, still much better, much faster. Each one took maybe 15 seconds, but the problem is I would much rather do this vertical with this sitting up, but I can't because I pre-attached the BMS, so I had to do it kind of sideways like this, and I was having solder sort of dripping down, and obviously trying to do it as quick as possible because I do not want to heat up these Ampace JP40s. But anyway, I think I got it done, and I think it's okay, and now I can not worry about it. Okay, so that's it. Marriage is complete. Not totally perfect, like most marriages are, but it should work, like hopefully most marriages do. Hopefully there's going to be no divorce. Yeah, definitely helps a lot to pre-solder all the thick wires and the connections, like I did. Almost no soldering, no heat into the cells, just this little connection on the bottom part. So marriage is done. Give it a day to dry and start on BMS. So this is part of the process that I don't think I've shown before. Getting ready to do the balance wires. Got to tape them in place here and then run everything. This is just doing extra insulation for safety because you got here B+, you got here B-, you got here metal. You do not want this touching across, so it's got like 3 layers of Kapton tape, green paper, and I just did a little extra pieces of FRP, Kapton tape, green paper. Just extra insulation, just in the very small chance that there's some impact where the bike is upside down and it shoves against here. You do not want these shorting across, so just take a little extra time. It's obvious, but make sure you insulate B+, B- so they're not touching the BMS. Okay, so that's how it's looking. Got everything ran. It's really hard to know the exact to the millimeter location where these wires have to be. Leave a little bit of slack. Like I said, this BMS is actually a little too long. Hopefully we'll be able to fit it in with a special 3D printed cap. It's a little longer, but anyway, yeah, first part of that's done. Like always, make sure you mark your wires so it's clear what goes to what. I know I'm not the absolute neatest wire organizer. I've seen people that do it just beautifully with surgical precision. Unfortunately, I'm not able to do it that cleanly, but main thing, she's going to be functional. And she is alive. Got all the balance wires done. Those went okay. It's always a kind of pain in the butt doing the ones that have to go on B+ and B- because then again have to use a big soldering iron. Always worry about that. Don't want to heat the cells. Anyway, did all the balance wires. Obviously before you connect, check everything, test with a voltmeter, make sure you got them in the right order. Balance wires go on, temperature, probes get connected. Sometimes it'll start just from that, but this time it didn't, so I had to do the little jump start thing there. And she's alive. So right now, this date and time officially starts the life of the battery pack. Gonna check Bluetooth. I really don't recommend though doing it this way. I mean, with this huge BMS, as you can see, this is how far it's going to stick out, front and back, past the case of the pack. Also, the other thing is I'm running 3 of the negatives off the BMS. It's got 6 because this thing is huge, so 3 are going on this side, 3 are going on that side. They're a little bit short. It's going to be fun trying to connect those. So in general, it's a lot more work doing this 340, 850 than kind of the standard 220, 550. Yeah, 550. So that's really the one to use unless you're just, needing to pull crazy amps. But we'll see how it comes together if I'm able to get it finished okay. So that's it. The pack is pretty much finished. And I know the question on your mind that you're asking yourself, so how does it rip? Let's see it working in the bike. How does it compare to that 40T pack? Well, I had planned to end the video with that, but I'm sorry to say that that section is going to be in a future video. The dirt build is set for a huge upgrade. this battery, the eBMX XLB60 motor, the eBMX swing arm. But lately I've been busy with a new street build. Yes, that video is going to finally come soon. And this bike here, the dirt build, is so balanced right now how it is that I just love it. And I don't mean balanced like in the air, although it is balanced well in the air. I'm talking about the synergy of all the components. Now, of course, nothing on this bike is state-of-the-art. Everything is a step down from state-of-the-art, or in the case of the brakes, 2 or 3 steps down from state-of-the-art. But it all just works so well together that I'm really in no hurry to just go ahead and tear it apart. So instead of changing 3 variables at once, I decided I'll just go ahead and change one now, the battery, and see to what degree that changes the feel and the ride of the bike. Then sometime soon, I'll complete the rest of the upgrades. I know I'm the only person probably in the world who bought a new eBMX motor 8 months ago and still hasn't installed it. Yeah, I know, it's sacrilege. So stay tuned to the channel. Soon will be coming a video of this bike ripping the new battery pack, and even sooner than that will be the new street build video. Thanks for watching.